study 9th standard ICSE chemistry chapter 3 water from Concise textbook. Dihydrogen oxide is its chemical name. Its molecular mass is 18 AMU. This is the atomic diagram. Introduction, mark it as read, not important. Cancel these paragraphs. Nature, it's colorless, odorless and tasteless. Boiling point is 100 degrees Celsius under normal pressure. The boiling point decreases as air pressure decreases. So on top of a mountain, say on Mount Everest, the boiling point is just 70 degrees Celsius. So it's important to use pressure cookers to cook food properly out there, because in the pressure cooker the pressure is more and hence boiling point will be higher and the water won't boil very quickly. The freezing point or the melting point of ice decreases with increase in pressure. It also decreases due to some dissolved impurities in it. Density of water is highest at 4 degrees Celsius, and that's 1 gram per centimeter cube. If the temperature falls below 4 degrees Celsius, then the density decreases, and that is why ice is less dense than water and it floats on water. Also, if you heat it above 4 degrees Celsius, once again its density will decrease. So in both cases, it expands. This is called anomalous expansion of water, because when you cool it, instead of contracting, it expands below 4 degrees Celsius. That's why there is a layer of ice on top of lakes in a frigid climate, which actually protects life, aquatic life, because the water under it doesn't freeze. Latent heat of fusion of ice, not important. Latent heat of vaporization of water, not important. And even specific heat capacity, not important. They will be taught in physics. You may want to know the definitions if the teacher insists that you should learn it. Latent heat of fusion means the amount of heat required by the ice to change into water. And the specific value is 336 joule per gram. Note that whenever there is a change in state, there is no change in temperature. Latent heat of vaporization means the amount of heat energy required to convert water into vapor at the boiling point, of course. And the specific value is 2268 joule per gram. Specific heat capacity is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius, which comes out to be 4.2 joule. In geography, you may have studied that places near the coastal areas, near the sea coast, they have moderate climate because of water's high specific heat capacity. It can absorb a lot of heat or give out a lot of heat, keeping the weather moderate. If you remember all this from geography, then that's suspect. Do you remember all the chemistry equations? Now, give reason. This is important. Water is a universal solvent because it dissolves a lot of solids, liquids, and gases. It dissolves ionic compounds, that is salts. It dissolves polar covalent compounds as well. And all this is because water has a high dielectric constant. Simply speaking, it has the ability to break bonds. It's a great divorcer. You can cancel this paragraph, even this one. Now, here's an experiment. If you boil tap water, you will notice that there are some impurities, proving that tap water has dissolved salts. Rainwater or distilled water is pure. These impurities are important because they are minerals essential for our growth. They add taste to water. There is some air dissolved in water as well. Now this is a good reason. In air, 21% of the air is oxygen. But if you look at the air dissolved in water, out of that 33% is oxygen, because oxygen is slightly more soluble in water compared to nitrogen. This experiment cancelled, all of this cancelled. Now this is a give reason. Why does boiled water have no taste? Because when you boil water, the dissolved carbon dioxide escapes. You see that the solubility of gases decreases with increase in temperature. And these gases like carbon dioxide gave drinking water the pleasant taste. It also gives a pleasant taste to your soft drinks, carbon dioxide. Once that escapes, it doesn't taste that great. Importance of air dissolved in water. Well, aquatic animals like fish obviously use this oxygen through their gills for respiration. Even aquatic plants, they use dissolved carbon dioxide for photosynthesis. It is also used by marine organisms to make shells. This Roman number 2, mark it as read, which means not very important. Now the B part. Definition of solution. It's a homogeneous mixture of 2 or more components, that is a solute and a solvent, whose composition may be gradually changed by changing the relative amounts of the components. For example, solute, take it as common salt, and solvent water. So that's salty water, that's a solution. This is the definition of solvent and solute. It's homogeneous because once salt is dissolved in water, you cannot identify the salt. It cannot be seen. You cannot distinguish between the solute and the solvent. On the other hand, if you mix sand to water, it is heterogeneous. You can easily see the sand particles separate from the water. Next paragraph cancelled. Now here are more examples. Solution need not be solid in liquid only. It can be liquid in liquid, like water and alcohol, they are miscible. Solid with a liquid, sugar solution. Liquid in a gas, soda water, like carbon dioxide dissolved in water. Solid with another solid, alloys. Example, brass. Now what is a true solution? If the particles of the solute are smaller than 10 raised to minus 10 meters, then they dissolve completely in the solvent. They can't even be seen with the help of a microscope. Then that is a true solution. The following are the characteristics of a true solution. It's homogeneous. It's truly homogeneous. Some solutions look homogeneous, but they aren't. For example, the air around you, it looks homogeneous mixture of various gases. But if it was a dark room and you allow a beam of light, sunlight, entering through the window, you would see dust particles in the beam of light floating in the air. Right now you can't see the dust particles, but in a beam of light you can. So it was not truly homogeneous. It's actually heterogeneous. So it's not a true solution. Air is not a true solution. It's a colloid. Similarly, blood is a colloid. If we use a microscope, we can see things not completely dissolved in it. But a true solution, it's clear and transparent. It does not scatter light, which is called Tyndall effect. And the components cannot be separated by filtration. You cannot get the salt from water just by filtering it. You'll have to do distillation or evaporation. If the solvent is water, it's called aqueous solution, and if it's not water, it's something else. It's called non-aqueous solution. Cancel the second point. Now we have a definition of dilute and conc. Dilute means it is a solution in which the amount of solute is rather less compared to the mass of the solvent, and it is a solution in which the amount of solute is relatively more for a given mass of the solvent. Do not use the word than in the definitions. These two definitions have to be written word to word like this. If you try to write in your own words, you may mess it up and you will not get marks. Now, next definition, saturated solution. A solution that cannot dissolve any more of the solute. Imagine you've added 5 spoons of salt in a glass of water and you stir it and it dissolves. And then you add a 6th spoon, but no matter how hard you stir it, it doesn't dissolve. That means the solution is already saturated. It can't dissolve more. Now there's an experiment, cancel that. Effect of cooling on a saturated solution. So imagine you have hot water. You see, a hot solvent will be able to dissolve more of the salt. So at room temperature, the glass of water dissolved 5 spoons of salt. Let's say at 80 degrees Celsius, that same glass of water was able to dissolve 7 spoons of salt. Now what if you cool that hot water? Then at room temperature again, it cannot continue to dissolve 7 spoons of salt. It can dissolve only 5 spoons of salt. So what will happen to the extra 2 spoons of salt? Well, it will crystallize out, and this process is called crystallization. So remember, if you want to convert a saturated solution into unsaturated solution, there are 2 ways. Number 1, add more solvent like water. And number 2, increase the temperature. There is also something called an super saturated solution. This is the definition. This first paragraph cancelled. Now imagine that when you cooled the water rapidly from 80 degrees Celsius to room temperature, and the salt dissolved was, let's say, potassium nitrate, something exceptional may happen. The extra 2 spoons of salt may not crystallize out. So now even at room temperature, we have forcibly dissolved 7 spoons of salt in water, more than its maximum capacity. It's like you are completely full. You've just eaten heavy lunch. But then the dessert comes, a sizzling brownie. You won't let the opportunity go away, will you? You'll still eat a couple of bites, even though you were saturated. So you are now super saturated. And this is the definition of super saturated. Next, cancel all of this, all of this. Mark the definition of solubility, however. It is the amount of the solute which can dissolve in 100 gram of solvent at that temperature. Next paragraph cancelled. Now factors affecting solubility. Size of solute particle, smaller the particle, more easily it will dissolve. Stirring, the more you stir it, the more easily it gets dissolved. Temperature, higher the temperature, more is the solubility. For most salts, there are some exceptions. Example cancelled. Solubility curve. This graph has some curved lines, which is called solubility curve. Mark the definition. It is a line graph that plots the changes in solubility of a solute in a solvent against changing temperature. So you can see potassium nitrate, initially it dissolved less, but as the temperature is increasing, its solubility is increasing very rapidly. On the other hand, sodium chloride's solubility does not change much with increase in temperature. And calcium sulfate is exceptional. After a certain temperature, you see that as the temperature is increasing, its solubility is decreasing. That means it will dissolve less in hot water. So it's an exceptional case. And you need to know the examples. But this graph is not important to draw. Mark it as read. They may give you this graph and ask you questions based on it. Questions like, give examples of substances whose solubility increases with temperature. Answer this. Sodium chloride increases very slightly. And examples of salts whose solubility decreases with increase in temperature. Example, hydrated calcium sulfate. CaSO4.2H2O. Hydrated means with the water of crystallization. And another example is calcium hydroxide, which is slaked lime. Anomalous solubility, all this is cancelled entirely. Solubility curve. What is the use of solubility curve? Well, mark it as read. It's useful to find the solubility at a particular temperature. Cancel all of this is cancelled, even this is cancelled. No numericals. Next, cancel this. Now, effect of pressure and temperature on solubility of gases in water or any liquids. Now, there is a Henry's law which says that more the pressure, more is the solubility of gas. For example, in soda water or in any beverage, cold drinks, you would notice that a lot of carbon dioxide or gas is dissolved in the soft drink under great pressure. But when you open the cap, you are releasing the pressure. It can no longer dissolve so much carbon dioxide, and that escapes out with a fizz called effervescence. So mark this as a GR. Temperature. Higher the temperature, lower is the solubility of gases. Now mark this as a GR. And that is why chilled soft drinks give out more fizz than room temperature soft drinks. And that's why we like chilled soft drinks. What were you thinking about? Go and drink some water. It's good for your health. It will prevent kidney stones. Don't worry, I'll wait. Next, crystals and crystallization. Crystal definition is it's a homogeneous solid of definite geometrical shape, like these ones. Fixed shape, well defined, not like talcum powder. It has symmetrically arranged smooth plane surfaces which meet, forming the sharp edges. But more important is the definition of crystallization, which I've already explained. It's a process by which crystals of a substance are obtained by cooling a hot saturated solution. Now we have these examples which are not important. Mark it as read. Cancel all of this. Cancelled. Next, hydrated substances. Certain salts have water of crystallization associated with them. They are called hydrated salts. Let's take an example of copper sulfate. Now, copper sulfate dot 5H2O means that 5 molecules of water are stuck in a weak bond. This dot means a weak chemical bond. It's not ionic or covalent, it's a weak chemical bond, and hence it's called hydrated copper sulfate. It's blue in color, so it's also called blue vitriol. It's also called copper sulfate pentahydrate. If you heat it, the water of crystallization will evaporate, leaving behind only copper sulfate. It's called anhydrous. Now, with the water of crystallization, it was crystalline. That's why it's called water of crystallization. And this is the definition of water of crystallization. It's IMP. Without the water of crystallization, it's no longer a crystal. It's amorphous, powdery. This is called just copper sulfate. It's white in color. Because of the water of crystallization, it was blue in color, but now it's white in color. So observations can be asked. What happens when you heat a blue vitriol? It becomes a white powder. From a blue crystal, it became white powder. And of course, steamy vapors were given out. Now, this table is IMP. You need to learn all of them. The common name, the chemical name, and the formulae. You can cancel a couple of them. By the way, green vitriol is iron 2 sulfate, heptahydrate, 7H2O. White vitriol is zinc sulfate, heptahydrate. My favorite is, you'll get to know in the test. If your teacher wants you to learn potash alum plaster of Paris as well, then do it. Then erase the cancellation. Next, more cancellations, cancelled. Anhydrous substances, which don't have water of crystallization. For example, sodium chloride never has water of crystallization, so it's anhydrous. Cancelled. Now, how can we convert a hydrated salt into an anhydrous salt? There are two ways. Number one, direct heating. And second, adding conch sulfuric acid, which is a dehydrating agent. How does that work? I'll teach that shortly. Now, there are many crystals in the world, which is not particularly because of water of crystallization. For example, sugar. Sugar is also a crystal, but it's not because it has any water of crystallization. No. So these are examples of crystals which have no water of crystallization. They are anhydrous, but not amorphous. Amorphous means powdery. Cancel all this. Now we come to a very important topic, efflorescence. Now, there are certain hydrated salts like sodium carbonate, decahydrate, also called washing soda. Even if we don't heat it, if we just expose it to air, it loses most of its water of crystallization. It becomes monohydrate. In fact, from crystalline, it becomes a powder. This phenomenon is called efflorescence, and such substances are called efflorescent salts. More examples: Glauber's salt and Epsom salt. Obviously, during humid conditions, efflorescence won't happen much because the air is already saturated with water vapor. You learn the equations as well. If the temperature is high and the air is dry, then efflorescence is more, marked as a GR. The opposite of efflorescence is deliquescence. Now imagine you have a salt like ferric chloride on this page here, kept here. After some time, you will notice that there is a solution, a saturated solution formed here, as if somebody has spilled water over it. But from where did the water come? Well, it was absorbed by the salt from the air, and it turned into a saturated solution. This property is called deliquescence, and it is maximum during humid conditions and minimum during dry conditions. All examples have to be learnt. A given reason can be asked: why should ferric chloride be kept in airtight bottles? Because if it isn't, it might absorb moisture from the air and become a solution. We don't want that. We want the salt to be intact. Now, I just said that sodium chloride is not a hydrated salt, and it is not even deliquescent. It doesn't absorb moisture. Yet the table salt in your kitchen does become moist during rainy season. Well, that's because the table salt does not have only sodium chloride. It has some impurities like magnesium chloride and calcium chloride, and they are deliquescent. So they will absorb moisture during rainy season, and the table salt will become a little moist. Cancel this paragraph. Next definition: hygroscopy. Now in deliquescence, the salts absorbed moisture and they changed their state. They became a saturated solution. But in hygroscopy, again, the substance will absorb moisture, but it will not change its state. For example, silica gel sachets are seen in new bags and new suitcases because they absorb the moisture and keep it dry, preventing fungal growth. But they don't change their state. They don't become a solution. Even quicklime, it is hygroscopic, not deliquescent. It will absorb moisture, but it won't turn into a solution. So that's the difference between deliquescence and hygroscopy. More examples: conch sulfuric acid, phosphorus pentoxide. Next, drying agents. So these hygroscopic substances can be used to dry things. So they're called drying agents. For example, in the lab, hydrogen is being prepared. Now, when hydrogen is being prepared, some moisture may also be with it. So we use a drying agent, in this case anhydrous calcium chloride, which will absorb all the moisture and dry hydrogen will be obtained. But make sure you use a drying agent which doesn't react with the substance which we want to dry. So this is the definition of drying agents, and they're also called desiccating agents, and these are the examples which you have to learn. Mostly these are the hygroscopic substances themselves. Now, dehydrating agent. Things like conch sulfuric acid, they have such high affinity for water that even if it is not present, they will create it and absorb it. For example, if you have sugar, the usual sugar, or even glucose, and you add conch sulfuric acid to it, it will break the bonds between carbon, hydrogen, oxygen. So only carbon will be left behind and water will be created, and then it will be absorbed by conch sulfuric acid. So this is called dehydrating agent. As a drying agent, conch sulfuric acid just did a physical change. There was no chemical reaction. But as a dehydrating agent, there is a chemical reaction. New substance is being formed. A black charcoal type of mass will be left behind. If you add conch sulfuric acid to sugar, try it. You can just borrow some conch sulfuric acid from school, bring it home and add it to sugar. But be careful, it's very corrosive. Do it under adult supervision only. More dehydrating agents, example, phosphorus pentoxide. Even here, there was a weak chemical bond, but conch sulfuric acid broke the bond, that's a chemical change, and absorbed all the moisture and converted the copper sulfate into white powder. And that's why the second point here was by using a dehydrating agent. Next, cancel this point. Cancel this, cancelled. Desiccator simply means a vessel in which a desiccating agent or drying agent is being used. Cancelled. Now, why don't we use quicklime to dry gases like HCl? Because quicklime is a base and HCl is an acid, they'll react. Or rather, we should use it for other bases like ammonia because they won't react. So that's a GR. Differentiate between drying and dehydrating agent. You have to learn this. And reaction has to be learned as well. Whatever is cancelled, you can cancel. Finally, the C part, soft and hard water. Water is said to be soft if it readily forms lather with soap. Sometimes, no matter how much you rub a soap in water, it doesn't lather at all. That must be hard water. That's the definition of hard water. It's because of some salts in it. Salts like bicarbonates, chlorides, and sulfates of calcium and magnesium. So totally there are 6 salts you have to remember. That is bicarbonates, chlorides, and sulfates of calcium as well as of magnesium. How do these 6 salts enter the water? The water in the well or the river or the lake? Well, through natural processes like rainfall falls on the soil and the rocks, and erosion happens and the minerals are drained away into the water body. Learn these 2 reactions. Cancel all of this. This is all geography. I don't have time for this. Now, there are 2 types of hardness: temporary hardness and permanent hardness. For example, water that contains only bicarbonates, that is hydrogen carbonates of calcium and magnesium, they are called temporary hard water. They don't have the chlorides or sulfates of calcium and magnesium. Because they have only bicarbonates, it's easy to remove the hardness. Just boil that water. The bicarbonates will decompose into carbonates, which will precipitate. You can easily filter it and throw it out. So now you are left with water which does not have this, and now it is not hard water, it is soft water. Now the soap will lather. Earlier the soap did not lather because when you use soap in water having these compounds, these salts, they react with the salt, with the soap, to produce some scum, some precipitates, which spoils the clothes as well. Hence it's important to get rid of them. Now water containing sulfates and chlorides of magnesium and calcium, that is these 4 salts, they can't be made soft by boiling. That's called permanent hard water. That can be removed by some other method. First of all, what is the advantage of hard water? Well, hard water has some minerals which are useful. It makes the water tasty, and the minerals are important for our growth of our bones and teeth. And also the hard water's minerals, they create a layer on lead pipes and prevent the poisoning of water by the lead pipes. Cancel the detailed explanation. But there are some disadvantages. First, it is not suitable for producing steam. If you try to boil it, then the salts will get deposited on that container, which will hamper the process. Cancel the details. Yeah, this boiler has some scales which have to be scratched off then. Cancel this, cancel this. Second disadvantage, right, Roman number 2, furring of the tea kettle. Same thing, if you use it to make tea in a kettle, the salts will sediment on the walls and this will again spoil the kettle. Hard water also spoils washing machines, etc. Third problem, it is not fit for washing purposes because lathering won't happen. In fact, if you try to wash clothes and the soap, which is some complex compound which you need not know, cancel it, reacts with the bicarbonates or any other hard water salt to form a precipitate which is called soap curd or scum, which will spoil the clothes. And the soap is also getting wasted. This is the formula of a normal soap. This is not the formula of Lux soap or any other fancy soap that you use. That formula you'll have to discover yourself. Now cancel this last sentence. Nowadays, we don't even care about soft and hard water because we don't use soap to wash clothes. We use synthetic detergents and they work efficiently and effectively in soft water as well as hard water. But just in case, what if the world runs out of detergents? Then we should know how to use soap and how to remove hardness of water. So let's study further. Cleansing action of soaps and detergents. Cancel this. If you want to make this your career, then please study this. Removal of temporary hardness. Well, by boiling, I've already explained that. If you boil it, it precipitates, filter it out, and you got soft water. There is a second method, Clark's process. So cancel that. There is one more process. Adding washing soda. Washing soda means sodium carbonate. Sodium bicarbonate is baking soda. Sodium carbonate is washing soda. What it does is it reacts with the salts and again creates precipitates which can be filtered and thrown out. So what is left is soft water. In fact, this method can be used even to remove permanent hardness. So this is a better method than boiling. Even if it's just temporary hard water, boiling is such a waste of fuel. Instead, just add washing soda. See, if it's a permanent hardness, then we can remove that sulfate of calcium or magnesium by adding the washing soda. Precipitates are formed, filter it, throw it out, you get soft water. Now continue using soap. Next, cancel all of this. Cancel this, cancel this.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.